Hey, good afternoon.
Good afternoon, Blake. How you doing today?
Not bad. Can't complain. What about you?
Peachy Keen, wonderful. Just happy to be
Nice.
here. I do want to speak to Rebecca because she's entering in here. Rebecca, you out there?
Yep.
Okay, I think you responded to Vera's question on cesium +1, xenon, and iodine -1. Do you remember that question?
I did not. I don't think.
That wasn't you. Was that Rebecca Hayes? Must have been then.
I definitely didn't. I haven't been on the forum.
No problem. In any case, if you guys ran across that, they all three of those have the same electron pattern. The cesium has lost its outermost shell, and the iodine has gained one to fill its outermost shell. So they all have the same electron configurations. The question was, which one has the biggest radius? In that case, cesium has the most protons, so it's going to suck its protons in, its electrons in closer. Iodine has the least amount of protons, so it's going to be the largest. Make sense, guys?
It does.
Amazingly enough, things do if you think about them. I got 1, 2, 3, 4, 5. Does anybody want to bet me that after next Tuesday, I'm going to have more attendance? No one wants to bet, huh? There's definitely going to be a lot more attendance after the during the gas laws phase. Anyway,
Well, after the gold and feather.
I'm sorry, Rebecca, I didn't hear you. Rebecca? Don't go shy on me, Rebecca. Okay, guys, we ready to get started? I'm noticing a certain lack of energy here.
Lego.
Ooh-wee. Okay. I specifically mark off one lecture day specifically to talk about empirical formulas, because as a general rule, these are going to be some of the hardest problems you encounter. And the reason for that is the fact that it's not always intuitive how to get the weights that you need to solve the problems. So I'm going to go through a whole bunch of problems here, and I'll get into a second slideshow. We're going to learn about percent composition from given weights, percent composition from an empirical formula calculation from masses, empirical formula calculation from reacted compounds, from percent composition, and then we're going to learn how to do the molecular formula calculation when we know the empirical formula and we know the molecular weight. Ooh, are we getting excited again? Try and control yourselves, everybody. Now, just a little bit of review. A molecular formula is a formula which has the actual number of each atom present within that compound. So if I'm talking about glucose, the glucose molecular formula is C6H12O6. By contrast, the empirical formula is the smallest whole number of atoms present in a molecule. So if I have C6H12O6, can I divide those subscripts by one common number?
6.
And I end up with CH2O. Okay? So, molecular formula, the actual number, empirical, smallest whole number ratio. Now, let's look at a compound. If I have one molecule of iron 2 chlorate, I'm sure you would agree that each molecule has one atom of iron, 2 atoms of chlorine, and 6 atoms of oxygen. But what if I have 6.02 times 10 to the 23rd molecules of iron chlorate. I would have 6.02 times 10 to the 23rd atoms of iron, or I would have 1 mole's worth of iron. If I have the same amount of chlorine, I would have 1.206 times 10 to the 24th atoms of chlorine, or 2 moles of chlorine. If I do it for oxygen, that would be 3.612 times 10 to the 24th atoms of oxygen, or 6 moles of oxygen. So if I'm looking at the subscripts within a compound, the subscripts also tell me what the molar ratio is of that particular compound. Am I saying stupid things yet? Specifically, this is why you don't carry over the subscripts when you're predicting reaction products. Because if you carry over the subscript for the chlorine and make NaCl2, you've changed the molecule. You no longer have salt, you have a different molecule with 1 sodium and 2 chlorine atoms. So let's get into this stuff from the start. Percent composition from given weights. If 11.17 grams of iron reacts with 4.80 grams of oxygen, what is the percent iron composition of this compound? Now guys, percent. What is percent? Per how many?
100.
Per 100. So basically what you are doing when you do a percent is you are taking the part, dividing it by the whole, then you're multiplying it by 100 over 100. Because when you divide the part by the whole, that's the amount of the parts in one of them. So what you're doing is you're multiplying the parts in one of them by 100 over 100. This way you get the parts per century. Does that make sense to you?
Yes.
If I was asking, instead of for percent, if I was asking for parts per million, I would still take the part, divide it by the whole, only this time instead of multiplying it by 100 over 100, I would multiply it by 1 million over 1 million. And that way I would get the parts in a million of the whole things. Does that make sense, guys?
Yep.
If it makes sense, Rebecca, great. You're going to solve the problem for me then. What is the part? If I'm asking for the percent iron composition, what is the part that I'm asking about?
You're asking out of the whole equation, how much does iron make up?
So what's the part?
Hold on. Let me pull up my periodic table.
No. Don't. You don't even need the periodic table at this point. Look at the screen.
So I add them together and I just divide by whatever that number is.
What are you dividing by whatever that number is?
Dividing by the iron, 11.17.
Okay, that's exactly what you're doing. The part is going to be the grams of iron. The whole thing is going to be the iron plus the oxygen. So if I was talking about something like batting averages, the way you calculate a batting average, it's how many times a person gets up at bat and makes a hit versus how many times they're at bat. So what you do is you take the hits and divide it by the number of times they go to the plate. So if a batter gets 99 hits every 300 at bats, he has got a hit percentage of 33%. So we're doing the same thing with percent composition if we're given the weights. I have 11.17, that's my grams of iron, that's the part. My whole thing is 11.17 plus the 4.80. So I divide the 11.17 by the total weight, the 15.97. I have my percentage. And multiply by 100, I have my percentage. Simple, guys? No one's making any comments, so I'll go with simple. Second part. What is the percent composition of iron 2 sulfate? Oh my God. Remember, guys, the subscripts tell me how many atoms there are. Do I know the atomic weights of each one of those elements?
Yeah.
So if I know the atomic weights of each one of those elements, all I have to do is find the atomic weight of iron and divide it by the molecular weight, and that will give me the percent iron. Sulfur, same thing. Oxygen, I'm going to have to multiply the oxygen by 4 because I've got 4 atoms in the molecule. But I take that part and divide it by the whole molecule, and I'm going to be able to get the weights. I add everything up. 4 oxygens, 1 sulfur, 1 iron. I add the whole molecular weight up, and I get 151.9 grams. So I get iron, I divide iron's atomic weight by the molecular weight, I get 36.77. I divide sulfur's atomic weight by the molecular weight, I get 21.10. Oxygen, I have to remember that I have 4 of them, so I have to multiply 4 by the atomic weight of oxygen. 4 times 16, 64. I divide that by the molecular weight, I get the percent composition of oxygen. The beauty of this is, if I have an empirical formula, I now know what the percent composition is. So if I give you a weight of iron sulfate, if I say there are 20 grams of iron sulfate, can you now tell me how many grams of that is iron?
Yes.
How, Blake?
You'd multiply it by the, well, I would do 0.3677, so I'd move the decimal over, but yeah, you basically just multiply it by the percent.
Yes, exactly. You're exactly right. Guys, there's no real need. Yes, if you get told to record percent composition, there is, you report it out as a percentage. But if you're getting asked a question like, how many grams of this compound is this element, then all you have to do is keep it as the 0.3677. Instead of being the percentage, that is known as the mole fraction. Okay? The mole fraction can then be multiplied by the total number of grams, and that will give you the grams of the element. It's just what you're doing with a percentage anyway. If you have a percentage, this percentage of 20 grams equals what? In order to get rid of the percentage sign, you have to divide it by 100. So it would be 0.3677 times the total weight will give you the grams of iron. Are we good with this? This isn't too complicated yet, is it? We good, guys?
Yeah, we good?
Good, good. All right. Sometimes you're going to have to calculate the percent that a part of a molecule contributes. This is basically what you were doing in the lab for this week, for last week. Wait, for this week, sorry. This week's lab was hydrates. Okay? Basically, a hydrate is a compound that incorporates water as part of its chemical structure. So, if we want to know how much of the weight is contributed by water, we need to know the entire formula. The entire formula is BaCl2 dot 2 H2Os. if I want to know what the water's contribution is, all I got to do is find out what water's formula is, find out what water's formula weighs, multiply that by 2, and then I'm going to divide it by the whole thing. And that will give me the percent of water in BaCl2.2H2O. Okay, water's molecular weight is 2 times 1.01, the hydrogen contribution, and 1 times 16. I add these two contributions together, I have 18.02, but there are 2 of them in that molecule. So water's contribution is going to be 36.04 grams. Okay? The BaCl2 contribution is there's 1 barium, it weighs 137.33, and there are 2 chlorines. Each of them weighs 35.45. So the barium chloride contribution is 208.23. To get the total weight, I have to also add in the water. So the total weight is 244.27. It now becomes a simple matter of taking the part, which is the water, dividing it by the whole molecular weight. I divide these 2 things out and I get 14.75. Are we good, guys? Okay. If I want to determine an empirical formula and I have the weights of the individual atoms, first step is always finding the weights of the individual atoms. Second step, you determine the number of moles of each atom. Third step, you divide by the smallest number of moles within the choices that you have. What that does is that gives you the molar ratio. Has anybody ever seen a chemical formula with the fraction of an atom? Does that exist?
No.
So if your ratio ends up having a fraction in it, you have to multiply that fraction by a whole number in order to get rid of it. And if you multiply it by the mole with the fraction, you have to multiply it by each one. Now, you guys, I'm sure you've seen the chart. Dr. Musgrave included a chart with the intro lab. And basically it said if your molar calculation ended up being 0.5, you multiply it by 2. 0.33, you multiply it by 3. 0.25, you multiply it by 4. 0.2, you multiply it by 5. 0.67 by 6, and it goes on from there. Okay, guys? You don't have to memorize that chart. Just start with 2. Try 2 and see if 2 will work. If 2 doesn't work, go to 3. If 3 doesn't work, go to 4. Eventually, one of them will work. Or by the time you get to 10, guys, go back and recalculate because you probably made an error somewhere. So again, the steps are 1, determine weights, which is going to be the hardest thing you have to figure out. 2, divide the weight of each element by its atomic weight to get moles. 3, you're going to divide by the smallest amount of moles. And 4, if one of the results turns out to be a fraction, multiply it by an integer to get rid of it. All right. A compound had 4.151 grams of aluminum and 3.692 grams of oxygen. Determine the empirical formula. Step 1's been given to us. We have the weights. Step 2, convert to moles. I divide the 4.151 by 26.98. This gives me 0.1539 moles of aluminum. I take my moles of oxygen, 3.692. Wait. Why did I use 16 instead of 32? Anybody know the answer to that? Why did I use 16 instead of 32? Isn't O2 32?
Oh, it is.
So why did I use 16 instead of 32?
Because there's only one oxygen. There's only one molecule of it?
Not molecule.
Or mole.
Remember, when we're doing empirical formula calculations, we are trying to relate the molar ratio of the atoms to one another. So since we're trying to relate the molar relationship of the atoms, every time you have a diatomic molecule, you are going to be dividing by the atomic weight, not the diatomic. Empirical formulas use atomic weights. When we get to stoichiometry, that's when you're going to need to use the molecular weight. So I have these two numbers out here. Jackson, which one do I divide by? Jackson? Dana, which one am I going to divide by? I think you guys are gone off and eating right now. Okay, Min, which one am I going to divide by? Which one did I tell you you're dividing by? I got three people. I've struck out. Min, you there?
Yeah, I'm here.
Okay, Min, which one am I dividing? Which one did I tell you you have to divide by?
The mole.
Which one did I say?
Divide mole.
Divide, which one, Min?
Number mole.
Which one am I dividing? I have the moles already, Min. I've got 0.1539 moles of aluminum and 0.2308 moles of oxygen.
0.1539.
Yes, you divide by the smaller one. I divide 0.1539 by itself. I get aluminum being 1. And then I divide 0.2308 by the 0.1539. I get 1.5 moles of oxygen. I have a fraction. I have to fix it by multiplying it by an integer. I'm going to start with 2. 2 times 1.5 gives me 3. I got a whole number. I'm happy. But if I multiply the oxygen by 2, I have to multiply the aluminum by 2 as well. So I get 2 moles of aluminum to 3 moles of oxygen, which is the same ratio as 1 to 1.5. So I know that now that I've solved that, I have 2 aluminums and 3 oxygens. My formula is Al2O3. Do we have any questions? This is the basic strategy for solving empirical formula problems. Find the weights, turn the weights into moles, divide by the smallest moles. If necessary, multiply by an integer. I got 0.2636 grams of nickel. I put the nickel in a crucible and heated it in air, and I formed 0.3354 grams of nickel oxide. What is the formula of my nickel oxide? Remember, I said the hardest part of this is figuring out the weights. Do I have the weight of nickel, guys?
Yes.
Okay, that means I got to figure out how to get the weight of the oxygen. Let's look at the nickel oxide. Is there anything else in that compound but nickel and oxygen?
No.
Remember, when I call something an oxide, that means that I have a compound whose anion is just oxygen and only oxygen. So, Rebecca, I have a compound that's just consisting of nickel and oxygen. I've told you how much reacted. How am I going to get the weight of the oxygen?
You subtract the nickel oxide with the nickel.
Indeed, that's what I'm going to do. I do that subtraction out. That means I have 0.0718 grams of oxygen. Guys, I have my weights. It's just going right down the strategy. What's the next thing I do, Rebecca?
Do you calculate the moles now?
Calculate the moles. Do the nickel out. I get 0.00491 moles of nickel. I do the oxygen. I get 0.00449. It doesn't matter. You can look at this and realize it's the same amount of moles. Therefore, it's a 1-to-1 relationship. My empirical formula is NiO. Questions? Any questions on this? Let's see who else is out there, if anybody else is out there. Joe, I haven't talked to Joe yet. Joe, what's your favorite number? Joe, you out there? Another person that's off snacking. Joe. Dana, you showing up?
Yes. Can you hear me?
Okay, Dana. What's your favorite number?
2.
2?
Yes.
Go bet it on the lottery this weekend.
Thank you.
You're not going to have much of a chance since you got to pull 6 numbers. Okay, Dana.
Yes.
I have a sample, and that sample was assayed to give me 26.57% potassium, 35.36% chromium, and 38.07% oxygen. I have no weights there, do I?
No. But they all add up to 100, right?
But they all add up to 100. Now, you said 2, right?
Yeah.
If you have 2 grams of your compound, can you tell me how many grams of the potassium you have of that compound?
Yes.
All you got to do is take 0.2657 and multiply it by 2, and you have the grams of potassium, right?
Yeah.
You could take the 0.3536 times the 2. That would give you the grams of chromium, correct?
Yeah.
And the same thing for the oxygen. Okay? All you have to do is pick a number and then apply the percentages to that number, and you can figure out your grams of your stuff. I'm lazy, Dana. I'm very, very lazy.
That's
Do
okay.
I want to choose 2?
No, you want to choose 1.
I want to choose 1?
Yeah.
I want to choose 100. I don't even want to bother with moving the decimal point. I'm even lazier than you are.
Okay.
So if I use 100, if I have my compound weighs 100 grams, then isn't 26.57 grams of that potassium?
Yeah.
And isn't 35.36 grams of that chromium and 38.07 grams of it oxygen?
Yep.
I've got my weights. I have my weights, guys. So I've got my weights now. Now all I have to do is what, Dana?
Divide by moles or molecular weight.
Divide by the molecular weight to get the moles.
Okay.
So I do this out. I get 0.68 moles of potassium, 0.68 moles of chromium, and 2.379 moles of oxygen. Now, Dana, finish it up for me. What do I have to do? What's the next step? I don't know is a good answer, Dana.
I multiply by whole numbers?
Nope.
Oh.
Do you have the ratio between them yet? You haven't done step 3.
You have to divide by the smallest moles.
Divide by the smallest moles. I do that for potassium, I get 1. I do it for chromium, I get 1. I do it for oxygen, I get 3.499. What am I going to have to do to the oxygen, Dana?
Multiply by 2.
Okay, guys, don't freak out about this. If you don't get an exact number, realize that there's a little bit of experimental error with everything. Like, for example, you multiply the 3.499 by 2, you get 7.998. It's not exact, or 6.998. It's not exactly 7, but it's close enough, guys. I would say if you're at 0.9, it's pretty much a good deal to call it at that point. So I multiply the oxygen by 2 to get 7. I have to do the chromium and the potassium as well. So I get an empirical formula of K2Cr2O7. Are we good, guys? Any questions so far? Another problem. Combustion analysis of naphthalene, a hydrocarbon, reveals 8.80 grams of carbon dioxide and 1.44 grams of water. Calculate the empirical formula of naphthalene. Now, this could freak you out if you weren't thinking. What you have to realize is that combustion analysis, I'm adding oxygen to the hydrocarbon and I'm making only H2O and I'm only making H2O and CO2. I'm converting all of the hydrocarbon, all of my naphthalene is getting converted to H2O and CO2. Now, Jackson, you there, Jackson?
Yes.
Okay, Jackson, can you see that all of the hydrogen that was within the naphthalene got converted to H2O? Can you see that?
Yes.
Can you see that all the carbon in naphthalene got converted to CO2?
Yes.
So if we can figure out from the grams of water how much hydrogen we have, then we'd have the grams of hydrogen. If we can find out from the grams of carbon dioxide how much carbon we had, then we have the grams of carbon. Can we get a mass percent of hydrogen in water, Jackson?
Yeah.
How am I going to do that?
They give you the grams for the two compounds, so you would just have to break those down into what makes up those compounds.
Give me an example.
So CO2, you would break it down into how much carbon is in CO2, or what the weight of the carbon in the CO2 is.
Give me.
Carbon dioxide weighs 8.8, so how much of that is carbon, and then how much of that is CO2.
Okay. Again, I need numbers, Jackson. I need numbers from you, Jackson. How am I going to get the carbon from the 8.80 grams of carbon dioxide? Can you figure out the percentage of carbon that's in every CO2 molecule, Jackson? Jackson?
Yeah, there's one carbon molecule for every oxygen.
Okay. Can you determine the percentage of carbon in carbon dioxide? Do you have the atomic weight of carbon? Can you look it up?
Yeah, it's 12.
Can you determine the molecular weight of CO2? What's oxygen weigh, Jackson?
It weighs 16 times 2 is 32.
Plus the 12 is?
Plus the 12 gives you 44.
So if I want the percentage of carbon in CO2, don't I just have to say 12 divided by 44?
Yeah.
And I take the 12 divided by 44, that gives me the percentage. I take that percentage, apply it to the 8.8 grams. Isn't that going to get me my weight of carbon?
Yes.
All right. Let's see who else I can pick on for a little bit. Let's go with Rebecca.
Yes.
Similar logic. Can you determine the percent of hydrogen in H2O?
Yes.
How do you do that?
You get the atomic weights and you
Well, what's the
have
atomic weight of hydrogen?
1.002.
Okay, so 1, you have to multiply it by 2, so hydrogen's contribution is 2 grams. What's the whole weight equal to?
18.
18. So all I'm going to do is divide the 2 by the 18. This will give me the percentage of hydrogen in H2O. Apply it to the 1.44 grams. I do it to the carbon. Carbon is actually about 27.3% in carbon dioxide. I multiply this by my 8.80 grams. This gives me 2.40 grams. I do my water. 2 divided by 18s, 1.11% or 11.1%. Multiply that by 1.44 grams. This gives me 0.160 grams of hydrogen. I now have my weights. What's the next step, Rebecca? I have my weights of hydrogen and I have my weight of carbon. What do I do now?
You add them together.
No.
Wait, you have your hydrogen and your carbon?
You have your look, didn't I just tell you if I have 1.44 grams of water, it's because I multiplied that by the percentage of hydrogen in water, I have the grams of hydrogen, right?
Yes.
I did the same thing for carbon in the carbon dioxide. I took the percentage, multiplied it by the whole weight of carbon dioxide. I now have the weight of carbon. So I've done the first part of my empirical formula problem. I found the weights. Once you find the weights, what's the second step tell you to do?
You divide by the smallest one?
Nope, you can't divide by that because you're dividing by grams. But what do you have to turn the grams into?
Oh, you turn into moles by
Turn it into moles. Turn it into moles. And if I do that, that gives me 0.2 moles for carbon, 0.160 moles for carbon. So I divide by the smallest one, which is the hydrogen molecular weight. I get 1.25 to 1. That is my molar ratio of carbon to hydrogen. Now, Rebecca, I got 1.25. How am I going to get rid of it?
Multiply by 4.
If I multiply it by 4, I have 5 carbons and I have 4 hydrogens. So my molecular formula is C5H4. We got that, guys? Now, if I told you that the molecular weight of naphthalene is 128, and I have the empirical formula, what is the molecular formula? Blake, do you remember way back at the beginning of the class when I was telling you how you get from molecular formulas to empirical formulas? What did you do?
Would you include the subscripts?
No, I'm just asking. When you went from a molecular formula to an empirical formula, you had glucose, C6H12O6. What did you do to get it to the empirical formula?
Oh, you just find a common, the least common denominator ratio?
And then what did you do with that least common denominator? What'd you do to the 6?
You divided.
Divided by 6. So
Yep.
when you're going from the molecular formula to the empirical formula, you are dividing by an integer.
Oh, yes, I follow. I got you now.
If you're going the other way, if you're going from empirical to molecular, you're going to be multiplying by an integer. Okay? We know if we have C5H4, if we have 5 carbons, that means that we have 5 times 12 or 60 contribution from the carbon, 4 times 1 from the hydrogen. My empirical formula weighs 64. I know that my molecular formula weighs 128. At this point, in order to find the molecular formula, I need to find out what I got to multiply the empirical formula by. I divide the molecular weight by my empirical formula weight, I get a whole number. That whole number is what we multiply the original subscripts by. I divide 128 by 64, I get 2. So I multiply the 5 by 2, and I multiply the H4 by 2. So this means my G. This means that my molecular formula has to be C10H8. Systematically, if we're trying to find molecular formulas when we're given the empirical formula and the molecular weight, we're given the empirical formula. So we're given the part that is the smallest ratio. If we get that number and we find the weight of the empirical formula, we can divide the molecular weight by the empirical formula weight. That will give us a whole number. We then multiply each of the subscripts in the empirical formula by that whole number. So if I take CH2O, that carbon's 12 plus 2 hydrogen, 14 plus 16 from the oxygen. I've got an empirical formula weight of 30.03. At this point, I divide the molecular weight by the empirical formula weight, and I get a whole number of 6. Now I've got the multiplier. I then take the multiplier number and multiply it by each of the subscripts in the empirical formula. The carbon gets multiplied by 6. 1 carbon times 6, I get 6 carbons. 2 hydrogen by 6, I get 12 hydrogens. 1 oxygen by 6, I get 6 oxygens. So that my molecular formula is C6H12O6. Questions, guys? As far as I know, those are the different types of empirical formula and mass percent problems that you're going to encounter. But they are going to get worded a little more difficultly. So we're going to have to figure out, I'm going to go through a couple more problems. That's all I'm doing today. I've got a half an hour left. So I'm going to go through some more problems, and hopefully this will apparently I zapped out of it earlier. Okay. Is everybody seeing the screen that says empirical formula and composition problems?
Yes.
Good, Rebecca. What is the mass percent of sulfate in aluminum sulfate? How are we going to solve this problem, Rebecca?
You're going to find the molecular weight for each of them. And then
Let's go
when you
for it.
add them, oh, Like, do it now?
Do it right now.
All right.
SO4, what's the sulfur weight? Do you have any idea?
No, but I can check right now.
Okay, fine. You'll get tired of checking after a while.
32.06.
Okay. And do you know what oxygen weighs?
16.
So 16 times 4 is 64 plus the 32.06. That gets me 96.06, right?
Yes.
Is that all of the sulfate in aluminum sulfate?
No, you have to multiply by 3.
So we get, yeah, I'm sorry, I can't do that one in my head. So 3 times 96.06 is 288.18. Okay? Now, what's left in the molecule that's not sulfate?
2 aluminums.
Do you know what aluminum weighs?
No. 26.9, so 27.
26.98. Close enough. 27's good. So I have to multiply my 2 aluminums. 2 times 26.98, that is aluminum's contribution. So I add the 53.96 to the 288.18. I get 342.14. And simply becomes a matter of dividing the sulfate contribution by the aluminum. Aren't you lucky I gave you a law question, Rebecca?
Very.
Okay, we're gonna go. Joe, you're out there, Joe?
Yes, can you hear me?
Yes, I can, Joe.
Good.
This actually is a practical question. The U.S. Food and Drug Administration recommends that an adult consume less than 2.4 grams of sodium per day. What mass of sodium chloride can you consume and still be within the guidelines?
2.4.
That's sodium. Sodium chloride weighs more than sodium, doesn't it?
Yeah.
So how are we going to figure out this problem?
Why don't you just find how much sodium chloride is, and then take out the sodium you can get per day?
Give me numbers. Do you know what, first of all, do you know what the formula for sodium chloride is?
It's something CL.
Okay. How about NaCl?
Yeah.
NaCl. Okay, so we have a formula. What can we do?
Okay. So you can find out sodium chloride, which is sodium's 22.98 plus 35.45.
Okay, that gives you 58.44.
Probably. And then once you do Na times 2.4, so whatever, like once you do 22.98 times 2.4, or no?
Nope. Okay, let's analyze the question a little bit, okay? The 2.4 is my part of the whole molecule, correct? Guys, isn't that
All right.
correct? So if I find out the percent of sodium within sodium chloride,
Okay, I get it now, yeah.
okay,
So I got to find the percent first and then multiply it by 2.4.
well, what you're going to do is you're going to divide the 2.4 by that percentage. Let's work this out, okay?
Yeah.
All right. To get the percentage of sodium in sodium chloride, I take the 22.99, divide that by the 58.44. This gives me 39.33%. Now, that's 39.33% of the whole number. That's what we're trying to find out. Do you see that, Joe?
Yeah, I see. Yeah, I understand that part. I
39
was just
point,
confused at the 2 point.
well, hold on a second. The 39.33% of the number we're looking for, that's equal to 2.4.
Okay.
Do you understand?
Okay.
Do you understand, Joe?
Yeah, you're trying to find out what other percent is of 2.4. I mean, yeah. So you're
So
pretty much going to
basically-
do 2.4 divided by.
Basically, what I'm doing is I'm taking my percentage of sodium within sodium chloride and I'm multiplying that by the weight of the sodium chloride that I don't know yet. But what I do know is once I take that percentage, the answer I come up with is 2.4. Okay? So I have 0.3933x is equal to 2.4. I divide the 2.4 by the 0.3933. This gives me 6.2 grams. You can consume 6.2 grams of sodium chloride and you'll still be within guidelines. If you don't like that, okay, let's think of what the 39.33 grams or 33.33% means. That means that there are 39.33 grams of sodium per 100 grams of sodium chloride. Joe, did that make sense to you?
Yeah, I understand it a little bit. Yeah, I get it enough. I think I
Okay.
can do it.
So if this is 39.33 grams of sodium in 100 grams of sodium chloride, I've got a conversion factor. So I have 2.4 grams of sodium. I multiply that by 100 grams of sodium chloride over the 39.33 grams of sodium. That will also give me the correct answer of 6.2. Either one of these ways works. They both work. Okay?
All right.
Blake. You're out there, Blake.
I am.
I have a silver coin that weighs 5.82 grams. Remember, coins are not pure metals. What I do is I take that silver and I dissolve it in nitric acid. Then I add sodium chloride and I get all of the silver to precipitate out as silver chloride. I then gather all the silver chloride, dry it down, and find that it weighs 7.20 grams. I need you to determine the percentage of silver that's in the coin.
Okay. We got the weight of the precipitate. So I feel like you'd have to do something with that.
Remember, where did the silver and the silver chloride come from? It came from the coin, right?
Mm-hmm.
So all the silver in the silver coin was reacted to make silver chloride. Does that help you a little bit?
Ah, yeah, it does, because that's a relationship. So then you could just take the atomic
Go ahead.
weight, the atomic weight of silver chloride, and then find out what relationship they have together, and then you could use that product answer to actually nah.
Let me ask you this, Blake. Can you get a mass percent of silver in silver chloride?
Yeah, absolutely.
All right. If you get a mass percent of silver in silver chloride, can you apply that to the weight of silver chloride and get the weight of the silver?
Yes.
Do that.
Okay.
Silver weighs about 107, chlorine weighs 35.5. So just tell me the numbers you got to do.
So it'd be like 140 grams.
Yeah, something like that.
140,
142.
something like that.
142.
Okay, so if we know that, then we could just divide the weight of silver by that. and that would get you your number once it's multiplied by 100. So that's a percent. So you take the percent.
All right, are you seeing the slide I have up here?
Yes.
Okay, so you got
Sorry.
75.265% of the silver chloride is silver. What are you gonna do with that number now?
I'm sorry, I missed that. What was it?
Okay, you have the percentage of silver in silver chloride is 75.265%.
Okay.
So what are you going to do with that 75.265%?
You're going to multiply that by 7.20 grams.
And that will give you the grams of silver, right?
Yes.
So once you have the grams of silver, then what are you going to do with the 5.42 grams of silver?
You're going to do something with it. I'm trying not to look ahead. It's very hard not to.
Blake, right now, out of 10 points, you probably have 7.
Okay, so I'm almost there.
6, 7.
Okay.
Do you know what the weight of the whole coin is?
We do.
Do you know what the weight of the silver is?
We do.
So how are you going to get the percentage of silver?
Well, if it's a silver coin, wouldn't it be like almost all silver?
Do we have the weight of the, again, Blake, do we have the weight of the silver?
We do.
Do we have the weight of the coin?
Yes.
So what do we have to do?
Divide it.
We have the weight of the silver, which is 5.42. We have
I mean, this is really easy stuff, but it's just stumping me on the spot. Like if I had like 5 minutes to write it out, I'm sure I could breeze through it, but.
Don't worry. I'm sure everybody else that's in this classroom right now is confused because of the way I'm trying to pull it out of you. I'm going to go back and explain it in a second, okay? So in order to get the right answer, you're going to take the amount of silver you got by determining what the silver chloride had in it. So that determines the weight of the pure silver. You just simply divide it by the weight of the coin, and the coin is 93.1% silver. So let's go back. Let's go back to the original question. Okay? I'm looking at this question. The first thing I have to see is that all of the silver reacted. So all of the silver in the coin reacted and made silver chloride, and that silver chloride weighed 7.20 grams. Okay? I have a formula for silver chloride. If I have a formula for silver chloride, remember at the very beginning of the class, I said if I have a formula, I can get a percentage of each element. So if I have silver chloride, I could take the silver atomic weight, divide that by the molecular weight of silver plus chlorine. That will give me a mass percent of silver. I take that mass percent of silver, multiply it by the weight of the silver chloride. That will give me my grams of silver. That grams of silver came from the coin, so I take the amount of silver, divide it by the weight of the coin. I have my percentage. Guys, is anybody confused by that? We have a test on Tuesday, so if this is confusing you, let me know, guys. I'm taking the crickets for being a positive response. So we're going to go on to the next question. Who wants to work it through with me? Guys, if you're working this through with me, this is giving you a logic that you're going to be able to use on the test question.
I can work it through with you.
Thank you, Dana. I have a piece of plumbing solder. Solder is just a metal it's a metal alloy that contains tin and lead. The solder weighs 3 grams. I first dissolve it in nitric acid and then treat it with sulfuric acid. This precipitates all the lead as lead sulfate. After I wash and dry it, the lead sulfate weighs 2.93 grams. Okay? I've removed all the lead from the liquid that is over top of the solid. But that liquid still contains tin in it. I take that solution, which contains tin in it, I neutralize it to precipitate out stannic acid. I then take the stannic acid and heat it, and I get back 1.27 grams of tin 4 oxide. What is the analysis of the solder as percent lead and percent tin?
Well,
You're doing Dana, you're doing the same problem that we just did the last one. That's your big hint.
okay. So we take the lead that was precipitated out.
As lead sulfate.
Yes. And we do sulfate and lead's atomic mass.
Okay. Lead weighs about 207 and sulfate weighs about 96.
So
You got 1 point so far, Dana.
thank you.
No pressure, no pressure.
So then we take the weight
Of,
of
does
lead.
anybody out there have a suggestion for her? Suggestion from anybody? Remember what we just did with the silver chloride. Dana,
Take
can
out
you,
the percent of lead.
what's that?
Well, maybe take out the percent of lead. Like, you want to find out the percent of lead in that?
There we go. Can you find the percent lead in the lead sulfate?
Yeah.
Okay. Once you find a percent lead in the lead sulfate, what are you going to do?
You take that. I don't know, because you took it out of the solder and it has tin and lead in it. So do you go back to the 3 grams yet?
Not yet.
Okay, then we
All right.
have,
Who was that, Joe? I think it was Joe that said that. Joe said, I'm sorry, it was who?
It was Joe, yeah.
It was Joe?
Oh, me.
Okay. Dana, didn't he say that you could get the percent of lead in lead sulfate?
yes,
Do you know how much the lead sulfate weighs?
you said like 94 plus 20 something.
No. Basically, I'm sorry, you jumped back and forth a couple times. All right.
Okay,
We can get the percentage of lead in lead sulfate by taking the atomic weight of lead, which is 207, and divide that by the total molecular weight, which is 207 plus sulfur, 32 plus 64 oxygens, which is going to be, I gotta look it up. So I've got the weight of lead is 207.20 divided by the total molecular weight, which is 303.26. That means the percentage of lead in lead sulfate is 68.324%. Would you buy that, Dana?
I'm buying it.
All right. Now, do I know the total weight of the lead sulfate that was collected?
Yeah.
So if I know the total weight of lead sulfate that was collected, and I know the percentage of lead in lead sulfate is 68.32%, can you tell me how much lead's there?
Yes. Multiply it by 2.93.
That's all I have to do. I have to get the percentage of lead that's in the lead sulfate, and I'm going to multiply that by 2.93. So that means I have 2 grams of lead. The solder weighed 3 grams. So I divide the 2 by 3, and I get 66.67% lead. Okay?
Okay.
Now, do we know how much tin is there?
Is there just tin and lead in the solder?
Ah, you don't know that, do you?
No.
So you could just say, okay, well, if there's only tin and lead in there, then it's got to be 33.3%. But you don't know that for sure. The only way you can check for sure is to use the other information that you were given. You were given that you have 1.27 grams of tin 4 oxide. Now, Dana, can you figure out the percentage of tin in the tin 4 oxide?
Yes.
How are we going to do that?
Yep.
Yep. The tin weighs 118.7 grams. Tin oxide weighs 150.69. So to get the percent of tin in the tin oxide, I divide the 118 by the 150, and I end up with 78.76%. Now, Dana, what do I do with that 78.76%?
You multiply it by the weight.
Multiply it by the weight. I've got 1.27 grams of tin oxide. All I'm going to have to do is I'm going to have to take the percentage of tin in tin oxide, and I'm going to multiply that by the weight of tin oxide. This gives me the grams of tin. Lo and behold, I had 2 grams of lead, 1 gram of tin. So as a matter of fact, it only had tin and lead in it. New problem. I have pure copper that weighs 3.178 grams. I heat that in a stream of oxygen until everything is converted to the black oxide. Now, what does the black oxide consist of? What elements?
Oxygen,
And
copper.
oxygen and copper. Anything else in there? Danny,
Black powder.
what's that?
Black powder?
Nope.
Nope. Okay.
It's got oxygen. It's the black oxide. What's it the oxide of? What did I heat?
Copper.
Copper. So my oxide consists of copper and oxygen. Anything else?
No.
No.
So if the black oxide weighs 3.978 and I started off with 3.178 grams of copper, can you tell me how much the oxygen weighs?
Yes. Just
How much
subtract
is
them.
it? Rebecca, how much is it?
Let me grab a calculator. You just subtract
no.
them.
0.8.
Huh?
0.8.
Okay.
This is the weight of, you have the screen, Rebecca?
Yes, I see.
This is the weight of the oxide. This is the weight of the copper. All you got to do is subtract the copper from the copper oxide. This gives you the weight of the oxygen. Now, what do? We want the empirical formula. What do we do, Rebecca? What's the next step? I have the weights. What do I do now?
Convert it to moles.
Convert it to moles. If I want the percent composition, I just take the weight of copper, divide it by the weight of the oxide. If I want the percentage of oxygen, the weight of oxygen, divided by the weight of the oxide. That will give me the percentages. But if I want the empirical formula, I'm going to take my weight of copper divided by my atomic weight. This gives me 0.05001 moles of copper. I have my moles of oxygen, divide that by 16, I got 0.0500 moles of oxygen. Now what do, Rebecca?
They both look, oh wait, yeah, they both look pretty equal. So would you even need to multiply?
At this point, not multiply, divide.
Yeah, divide, I mean.
At this point, you can look and say, okay, we got equal number of moles. So my formula is going to be CuO. Okay?
Yep.
This one, okay, hard problem because you got to think about this. This is the last problem I'm going to work for you guys. I've got a compound that consists only of carbon, hydrogen, and oxygen. When I combust that compound, I make 2.445 grams of carbon dioxide, and I make 0.6003 grams of water. What is the empirical formula? Do you remember how we did combustion problem? How we did the combustion problem? Jackson, do you remember how we did that? I think you worked it actually.
No, I didn't. But it was just the products of a combustion reaction are H2O and CO2, right?
Yes. Okay. Do you remember how we did that? You got 2.44 grams of carbon dioxide. Can you figure out how much carbon there is there?
Yes.
How do we do that?
Weight of carbon's 12.
Yep.
Oxygen is 16, right?
But how many oxygens do I have in CO2?
There's 2, so it's 32.
So 32 and 12 is 44. Carbon weighs 12. So in order to get the amount of carbon, all I have to do is take the 44 divided, or take 12 divided by 44. That gives me the percentage of carbon. I multiply that by the weight. This means I have 2.40 grams of carbon. Hydrogen, I'm going to do the same thing. 2 grams of hydrogen divided by 18 grams of H2O makes 11.1% times 1.44. I got 1.60 grams of hydrogen. Now, there's a problem though. We still need the weight of the oxygen, don't we? Now, you might think that, okay, well, I got the weight of my carbon by multiplying by the mass percent of carbon in the CO2 to get my grams of carbon, and I did the same thing for hydrogen. Why can't I just do the same thing for my oxygen? Does anybody see why that would be wrong? Think about the combustion reaction. What are you adding in a combustion reaction?
Heat.
And You have the hydrocarbon, the C, the H, and the O compound. What are you adding to that to combust it? Come on, guys. How did I tell you? What did I tell you to recognize a combustion reaction? A hydrocarbon plus what other thing?
Oxygen.
Oxygen. So you can't solve for the weight of oxygen this way because you're adding extra oxygen into the CO2 and into the water. But there is something you can do. You've got the weight of carbon, you got the weight of hydrogen. Don't you have the weight of the whole compound? All you have to do is take the weight of the whole compound, subtract the weight of the carbon, subtract the weight of the hydrogen. That gives you the weight of your oxygen. So I have 0.0617 grams of carbon, grams of hydrogen, 0.6673 grams of carbon, and 0.0888 grams of oxygen. Again, this is going to be just a normal thing. From there, we have the grams of our stuff. Once we have the grams of the stuff, what we have to do is we have the grams of the stuff, we get the moles. Then once we get the moles, we divide by the smallest. So the smallest one is going to be the oxygen. I divide the oxygen into the carbon. I get carbon's ratio is 10:1. I divide the oxygen into the hydrogen. I get the hydrogen ratio of 12:1. So my empirical formula is C10H12O. Okay, guys, that's all the further I'm going to go. I think I only skipped one problem, and the last one problem within here, and this last problem. Yeah, let's go ahead and do this real quick. How much K2O could be produced from 500 kilograms of potassium? What's the ratio of moles of potassium to potassium oxide? The moles of potassium to K2O is 1:2, right? So all I have to do is find the grams of, I have to find the moles of potassium, and I multiply that by the 2K and K2O. This means I can produce twice as many moles of K2O. Then I take the moles of K2O, multiply that by the molecular weight. This gives me the grams of K2O. Okay, ladies and gentlemen, this is what stoichiometry is all about, and it's what we're going to get into the period after the test. Okay. I've gone a little bit over, I'm sorry. If you want to stay, I will talk about the test a little bit. Nope, that's not what I want. That's not what I want either. I'm out of there. Hold on a second, I got to sneak back into the course thing. Do you all have any questions while I'm looking up the course? You have nothing, no questions, so we can go ahead and go home?
My brain is dead.
Okay.
You did say something about the test.
Yeah.
What?
Okay. First of all, I want to point out something to you. I need to do this. Share screen. Okay. Are you seeing the screen right now, the course screen?
Yes.
Go into content. I made this up this afternoon. Guys, please forgive me. I did this real quick this afternoon. I put the answers right after the questions, but I did it real quick. Be kind. If you find a wrong answer, email me. Don't yell at me for the wrong answer. Okay, practice test. I go through and give you questions with the subsequent answers right behind it. Fair enough, guys? Are we good? Good with that? I'm getting no response here. Are we really that dead tired? Did I lose you guys?